Name the following compounds indicating stereochemistry where possible. So this is compound A. How do we name this compound? The first thing is to determine the configuration over here. So the fluorine is 1, then we have CH2CH2Br, and then we also have a CH32OH. So here is 2, and then this is 3. But the proton is pointing towards us, and therefore this is an S configuration. Now, let's try naming this compound. So you see that this compound is an alcohol. It will be named as an alcohol. Let me expand the drawing of this compound down here. So it will look like this. And down here is a CH2, CH2, and then a Br. And then this side is a C. Then we have CH3 here. We also have CH3 here, and then an OH. And then we have a fluorine group here, and then a proton here. But we've determined, so let's try and determine the numbering of the carbons. Because it's an alcohol, we'll give precedence to the OH. And therefore, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So it is a pentanol. And actually it is a 2-pentanol because the OH is on carbon number 2. However, at carbon number 3, there is an S configuration there. And then the bromine is on carbon number 5. So we have a 3S configuration. Then the bromine, in terms of alphabet, the bromine comes first before this methyl substituent. So we have 5 bromo. Then this methyl substituent, which is a 2-methyl. Then the parent chain is pentanol. So 2-methyl, 2-pentanol. Showing the position of the OH group. Let's name this compound. So you see that this is a substituent on a substituent. Now let's count the number of carbons on the straight chain. It is 1, 2, 3, 4, 5. And let's count the number of carbons on the cyclic ring. It is also 1, 2, 3, 4, 5. When there is an equal number of carbons on the straight chain and the cyclic ring, precedence is given to the cyclic ring. And therefore this will be named as a cyclopentane. And then the cyclic ring is the parent chain. Now, when you consider the straight chain, it is a substituent on a substituent. We have an ethyl group that is on this substituent with number 1. So we have 1. Then all of that is joined to the cyclic ring at carbon number 1. So it is 1. Then when you want to name a substituent on a substituent, you put that in a bracket to show that it is a substituent on a substituent. So this ethyl is on carbon number 1. So 1 ethyl. Then there is a propyl group here. 1, 2, 3. So this is a propyl. So 1 ethyl propyl. Then it is on a cyclopentane. So cyclopentane. So this is the name of this compound. Let's come to this one. So with this one, we need to show the isomerism. And this is a geometric isomerism, which is cis and trans isomers. So let's try and number the carbons. This is 1, 2, 3, 4, 5, and 6. So you see that we have 2 substituents that are on 1, 4, which is one is on a wedge bond and the other is on a dash bond. So this is a trans isomer, and therefore we are going to have a trans. So we know that this molecule will have to begin with a trans, and the parent is also a cyclohexane. Then apart from that, so this group is the isobutyl group. This is an isobutyl group. So we also have an isobutyl on carbon number 1. So isobutyl group on carbon number 1. And we have this ethyl group on carbon number 4. And then so we have 4 ethyl. So let's add the names and name them. So in terms of B and E, alphabetically B comes before E. So we will have trans and then 1 isobutyl, and then the ethyl is on carbon number 4, so 4 ethyl and cyclohexane. And that is the name of this last molecule. Name the alkanes corresponding to each of the following and identify stereochemistry where possible. So let's see if there's stereochemistry here. If we take the carbon in front, there are 2 groups that are the same. So there's no stereochemistry around the carbon in front. And if we take the carbon at the back, there are 2 groups. This CH3 is equal to this. And therefore, there is no stereochemistry in this molecule. Nonetheless, let's name the molecule. So if we were to expand it, you see that this carbon number 1, carbon number 2, carbon number 3, the one at the back, and carbon number 4. So it is a butane. However, we have a CH3, a methyl group on carbon number 2, which is the carbon at the back. And therefore, the name of this molecule is a 2-methyl butane. So let's consider this molecule. Now, let's determine whether there is a stereochemistry somewhere. You see that the carbon at the back is a CH3, and this carbon also bonded to a CH3, and therefore they are equal. So there's no stereochemistry with reference to the carbon in front. And the carbon at the back, there are at least 2 protons on it, and it also does not have stereochemistry. So we'll just have to name this molecule like that. And the carbons are this carbon number 1, carbon number 2, and the one at the back is carbon number 3. And then we have an iodine group, which is on carbon number 2. And therefore, this is 2-iodo, and the whole molecule is made up of 3 carbons, so that is propane. So this is 2-iodopropane. Give the IUPAC names of the following. So we have this molecule. Let's first determine the stereochemistry in this molecule before we name it. So the configuration here is 1, and then the ethyl group is 2, and this is 3, and then the proton is 4. So 1, 2, 3 is going in this direction, but the proton is facing us, and therefore this is an R molecule. So let's go ahead and name it. So we can see that there are 4 carbons on this molecule, carbon number 1, carbon number 2, and there are also 2 carbons here. And on carbon number 2, we have a chlorine substituent on it. So we need to first indicate the configuration in bracket, which is a 2R, then 2-chloro. The number of carbons are 4, so 2-chlorobutane. So the name of this molecule is 2R, 2-chlorobutane. Let's come to B. Is there any stereochemistry in the molecule B? You can see that this is a chiral center because it has 4 different atoms connected to it. This atom is different from this one, and then also different from the fluorine group, and there is a proton at the back. So that is a chiral center. You can also see that there is also another chiral center here. this fluorine, this carbon is different from this one, which in turn is different from this CH3, and therefore there is also another chiral center here. But this is not a chiral center because there are two methyl groups, and this is not also a chiral center because there are two protons and there are also two protons here. So we have two chiral centers. So let's determine their configuration. So let's start from this one. Let me show the proton at the back here. So this part is 1, but this is a CH2. However, this is CH linked with a CH3. So this is number 2, and then this is number 3. However, because this is in the plane of the molecule and this is pointing away from us, then it implies that the proton is pointing towards us. And since the proton is pointing towards us and the configuration is going this way, we need to reverse it. So this part is an R configuration. This CH3 is pointing towards us, and this is in the plane of the molecule. It implies that the proton here is pointing away from us. So there's a proton here. Let's go ahead and determine the configuration. So here is 1 because it is a CHF, and here is a CH3. And this is a CH2, which is linked with this carbon. So CH2CH. Therefore, this part is 2, and this is 3. So it is going in the clockwise direction, this direction, and then the proton is pointing away from us. So the configuration here is also an R. Now let's go ahead and determine the numbers on the carbons. So we'll give precedence to the fluorine group because it is the most bulkier group than the CH3. So here becomes 1, then this is 2, 3, 4, 5. So 5 carbons, and therefore the parent name is a cyclopentane. So let me write it wrong. This is a cyclopentane. That is the parent name. And then we have 2 methyls on carbon number 4. So 4,4 dimethyl. Then apart from that, we also have another methyl on carbon number 2. Therefore, it is rather a 2,4,4 trimethyl because there are 3 carbons. So here's a trimethyl. And we have a fluorine group which is on carbon number 1. So 1 fluoro. Let's write the name. So but we need to show the configuration in brackets. So let me write the name on top here. So the configuration, you see that we have 1R and then a 2R. So in bracket, we have 1R, 2R, and then this is 1 fluoro because there's a fluorine group. 1 fluoro, and then 2, 4, 4 trimethyl cyclopentane. So that is the name of this molecule. It is a 1R, 2R, 1 fluoro, 2, 4, 4 trimethyl cyclopentane. Let's come to this side and let's name this molecule. Now, there is no chiral center in this molecule. This carbon has 2 protons. It cannot be a chiral center. And this carbon has 2 methyls, at least 2 methyls. It can also be a chiral center. And therefore, the name of this molecule is straightforward. So the number of carbons are 1, 2, 3. 3 carbons, so it is a propene. And then we have an iodine substituent on carbon number 1. And then we also have a dimethyl on carbon number 2. So it is going to be 1 iodo. And then we have a 2,2 dimethyl propane. Let's go ahead and name this molecule as well. So let's determine the parent chain. Starting from here, let's start from here. So this is carbon number 1, carbon number 2, carbon number 3, number 4, and then number 5. So the parent name is a 5 carbon, which is a pentane. 5 carbons, which is a pentane. Then we have bromine on carbon number 1. Then we have 3 methyls. One is on carbon number 2, the other is on carbon number 3, and then the last one is on carbon number 4. And therefore, it's going to be, but let's see if there are chiral centers here. You can see that this is a chiral center, and this one is also a chiral center, and that those two are the only chiral centers in this molecule. Let's determine the configuration over here. So you see that this is not 1, this side, this is 1, and then this is 2, and then this is 3. So it is pointing the clockwise direction, R, but the proton is pointing towards us, and therefore this is an S configuration. And let's come to this side as well. So you can see that at this side, this is carbon number 1. Number 1 is here, and then this one is number 2, and this is number 3. So it is moving in the anti-clockwise direction, which is an S. However, because the proton is pointing towards us, therefore we will have to negate the configuration, and that will become an R. So we have a 2S 3R configuration, and 1 bromo, because there's a bromine on carbon number 1. So 1 bromo, and then the substituents are a methyl on carbon number 2, 2 methyl. There's also a methyl substituent on carbon number 3, 3 methyl. There's also another substituent on carbon number 4, 4 trimethyl pentane. So that is the name of this compound. Methyl propyl ether and diethyl ether are examples of A, chain isomers, B, position isomers, C, metamers, and D, functional isomers. So what is the correct answer? Let's first explain what are chain isomers. However, let's just draw the structures of methyl propyl ether and then diethyl ether. So this is a propyl. So we first need to draw a propyl, then we'll draw a methyl. So this is methyl propyl ether, and then this is the structure of diethyl ether. So let's start from the metamers. What are metamers? Metamers are isomers with the same molecular formula, but different alkyl group around the same functional group. So metamers are also known as functional isomers. So what it means is that, for example, if you have a propanone and then you have a propanyl, these two are metamers and they are also functional isomers, because the position of the oxygen here is on carbon number 2, and the position of the oxygen here is on carbon number 1. So 1 and 2 are different. However, they are isomers of the same molecule. So they are functional isomers, and metamers are also functional isomers. And therefore, methyl propyl ether and diethyl ether are both metamers. They are also functional isomers. Now let's come to positional isomerism. What are positional isomers? They are constitutional isomers that have the same functional group, but they differ from each other in the position of the carbons to which they are bonded to. You can see that this is on carbon number 2. This is 1, 2, 3. and then this is on carbon number 1. This is 1, 2, 3. So carbon number 1 is bearing a double bond O. Carbon number 2 is bearing a double bond O in this case. So you can see that in diethyl ether and then methyl propyl ether, here the oxygen is sandwiched between carbon number 1 and carbon number 2. And in this case, the oxygen is sandwiched between carbon number 2 and carbon number 3. So this is a clear example of positional isomers. I didn't show the metamers and functional isomers with the diethyl ether. So let me show that. So you can see that in terms of functional isomers, they all have an oxygen that is sandwiched between methyl groups. However, this one is between carbon number 2 and carbon number 3, and this one is between carbon number 1 and carbon number 2. That is why they qualify as both metamers and functional isomers. And then the last one is chain isomerism. So what is chain isomerism? So chain isomerism occurs when two compounds have the same sort of chemical formula but distinct primary chains. So these have the same chemical. For example, let us consider 2-methyl-butane, and let's consider 2,2-dimethyl-propane. You can see that these are 5 carbons, and this one is also 5 carbons. So these are these are chain isomers because they only differ from each other along the chain. This methyl substituent is on carbon number 2. But here, on carbon number 2, it has 2 different substituents, a methyl group and another methyl group. So these are chain isomers. Now let's come to the diethyl ether and methyl propyl ether. You can see that along the chain, this one has an oxygen between carbon number 1 and carbon number 2. And this one has an oxygen between carbon number 2 and carbon number 3. So they are also chain isomers. And therefore, methyl propyl ether and diethyl ether are all of the above. Calculate the specific rotation of a solution of 5 grams of nicotine in 100 ml of ethanol at 20 degrees, taken in a 1 decimeter tube. The observed rotation is minus 8.45 degrees. So the mass that were given was 5 grams, and the volume is 100 ml. Therefore, you can calculate concentration, which is equal to mass over volume. So this is equal to 5 grams divided by 100 ml. And this is equal to 0.05 grams per ml. Now, the observed rotation that we're given is minus 8.45 degrees. And so we can go ahead and calculate the specific rotation. However, we're given a path length L of 1 decimeters, but we know that the specific rotation is equal to the observed rotation over concentration times the path length. So the observed rotation is minus 8.45 degrees divided by a concentration of 0.05 gram per ml, and then a path length of 1 decimeter, so times 1. And that will give us a specific rotation of 169 degrees. Minus 169 degrees. Tetracycline is called a broad spectrum antibiotics because it is active agent against a wide variety of bacteria. How many optical isomers does tetracycline has? Determine the configuration RNS on all asymmetric carbon centers. Identify all the sp2 carbons in tetracycline, and then circle and name all the functional groups present. Let's start from A. How many optical isomers does tetracycline have? The number of isomers that a molecule has is given as 2 exponent n, where n is the number of chiral centers in that molecule. So the first thing will be to determine the number of chiral centers in this molecule. So you can see that this carbon has 4 different groups attached to it, and therefore it is a chiral center. And you can see that this group is different from this one, which is also different from this one. Therefore, this is also a chiral center. And you can also see from here that this group is different from this one, which is also different from this. So this is also a chiral center. And then this group is different from this one, which is also different from the imine group. And therefore, this is also a chiral center. And you can see that there's also this chiral center, which is over here, because this group is different from this one, which is different from the OH. So how many chiral centers in all do we have? Sorry, I made a mistake. I think there is an alkene, a double bond here, and then there is also an OH here. So you see that tetracycline has 5 chiral centers. And because it has 5 chiral centers, therefore the number of optical isomers are 2 optical isomers. Is equal to 2 exponent 5. And 2 exponent 5 is equal to 32. So tetracycline has 32 optical isomers. And it says that we should determine the configuration R and S on all the symmetric carbon centers. So let's start with this carbon center. The OH is 1. Then this side is number 2, because this is a double bond. Precedence is given to a double bond than a single bond. And then this side is number 3. And then this is number 4. So you can see that the least group is pointing away from us, and then it is going in the anti-clockwise direction, and therefore this carbon center is an S configuration. Let's come to this one. You see that there is a proton here. So this side is a 1, and then this is 1, and then this is 2. This side is 1 because this carbon has a double bond, so we'll give precedence to this carbon. This is number 1, this is number 2, and then this is number 3. So it is going in the anti-clockwise direction, and therefore this carbon is also an S. Let's come to this chiral center. So with this chiral center, this is 1 because this carbon is bonded to an OH group. And then this is 2. And this is 3. A proton is pointing away from us. Therefore, this is also an S in the anti-clockwise direction. Let's come here. This is 1. And then this is 2. And then this is 3. So we have a proton here. Because this is in the plane of the molecule and the nitrogen is pointing away from us, then it means that the proton is pointing towards us. And because the proton is pointing towards us, we have to reverse configuration. Therefore, this is also an S configuration. And then let's come to the last one, which is this chiral center. So this is 1, and this is 2, and then this is 3, and then this side is 4. So it is moving in the clockwise direction. But the least group is in the plane of the molecule. So we need to swap 1 and 4, and then 2 and 3. So this side becomes 3, and this becomes 2, and then this becomes 4, and this becomes 1. So at the end of the day, it is 1, 2, 3, 4, which is going the anti-clockwise direction, and therefore the configuration here is also S. So you can see that the configuration in tetracycline is S configuration. All the 5 chiral centers in tetracycline are S. And the C part says that we should identify all the sp2 carbons in tetracycline. So in identifying the sp2 carbons, what we need to consider is the carbon double bond. So you see that this carbon is doubly bonded. So this is a double bond. This also. So all the carbons that are doubly bonded to each other are sp2. So this is one of them. This is the other. Then this is the third, the fourth, the fifth, and then the sixth. This one is also an sp2 carbon. This is an sp2 carbon. This is also sp2 carbon. So let me differentiate between that and the chiral centers by putting the asterisks circles. This is also sp2 and sp2. And then this is an sp2 carbon. This is also sp2 carbon. And then this is also an sp2 carbon. And then the last part of the question says we should circle and name all the functional groups present. So you can see that this one, straightforward, is an arene group. So A, let me write it here. A is an arene. And then apart from that, we have this group here. We have this group here. B is an alcohol. Apart from that, we have an amine functional group on D. So D is an amine. Then apart from the amine functional group, we also have an alkene at this point. So let's say F. F is an alkene. Then the last functional group is this functional group. G is an amide. So that is an amide functional group. This functional group is an amide. So these are all the informations to obtain from tetracycline. So assign R and S to the following compounds. You can see that this is a Fischer projection. So this is a triple bond. Triple bond, we give precedence to a triple bond over a double bond. Therefore, this is 1. And then this is 2. And then this is 3. And then this is 4. So this is 1, 2, 3. It is an R. Because the least group 4 is pointing away from us. So this is an R. Let's come to the B part. So we have this isopropyl group here. So that side becomes 1. And then we have the propyl group, which is number 2. And then the ethyl is number 3. And the methyl is number 4. So you can see that it is in the anti-clockwise direction. And therefore, this configuration is an S configuration. Let's come to the side. So we give precedence to a double bond over a single bond. So therefore, this is carbon number 1. This is 2. And this is 3. And then this is 4. So you see that this one too is also moving this in this direction. Therefore, this is also an S. Convert the following structures to Fischer projections. So let's start with the first one. This is this first molecule. So this is the carbon. This phenyl group is pointing away. So the phenyl group is pointing away. Let me represent it with a pH. pH for the phenyl group. And then we have this ethyl group, which is also pointing away. So CH2CH3. And then we have this proton, which is pointing towards us. So there's a proton here. And then there's a CH3 over here. So what we need to do is to draw the Fisher projection. So in terms of the Fisher projection, you know that the vertical line, the groups on the vertical line are those pointing away from us. And therefore, the phenyl group. So let me draw the Fisher projection here. So in terms of Fisher projection, the groups that are pointing away from us are on the vertical line. And therefore, the phenyl group will be on the vertical line over here. And then the CH2CH3 will be down here, which is the ethyl group. And then the proton, which is pointing towards us, will be on the horizontal line. And then the CH3 will also be on the horizontal line. So let me color this well. So this is CH3 on a wedge bond. So let's determine the configuration here. So here's 1, this is 2, this is 3. It's going anti-clockwise, but the proton is pointing towards us. And therefore, this is an R. Let's determine the configuration here. This is 1, this is 2, and this is 3. So it is also pointing this way. Now the proton is pointing towards us. And therefore, this is also R configuration. Now let's come to this molecule. So let's draw it in terms of Fisher. So the proton is pointing towards us. So the proton is here. And then this NHCH3 is also pointing towards us. So NHCH3 is pointing towards us. And then this group is on the dash bond, CH3. And then the ethyl group is also on a dash bond, CH2CH3. Now let's draw the Fisher projection. So the group pointing away must be on the vertical axis. And therefore, here's a CH3, and this is a CH2CH3. And then the groups that are pointing towards us, the proton is here. And then the NH3, it's also here. So let's determine the configuration on this molecule. This is 1, this is 2, and this is 3. The proton is pointing towards us. It is going this way. So this is an S molecule. Let's determine the configuration over here. This is 1, this is 2, and this is 3. The proton is not pointing. The proton is pointing towards us, and this is an R position. The proton is pointing towards us, and this is an R. But then, because we are converting to Fisher projection, we must not lose the configuration, and therefore we need to do something about this molecule to turn it into an S. So let me flip this to outside. Let me flip the proton and then the NHCH3 group. When we do that, we will alter the configuration. So I'm going to draw this. So let me do it here. So I'm going to draw this so that the proton comes here, and then the NHCH3 will come here, and here's a CH3, and this is a CH2CH3. So let's determine the configuration in this case. This is 1, this is 2, and then this is 3. The proton is not pointing towards us, and therefore this is an S. Norethindrone is a synthetic hormone with in oral contraceptive. Indicate with asterisk the chiral centers in the hormone shown below. How many optical isomers are possible with norethindrone? So we must first indicate the chiral centers. So you can see that if we consider this carbon and this carbon are different, and it's also different from this. So this is an optical center. And if we consider this one, this carbon and this carbon are also different, and it's different from this proton, and which is also different from this carbon. So this is also an optical center, as well as this one as well. It is also an optical center. This is also an optical center. And then this is also an optical center. And then finally, we can see that this is also an optical center. Sorry, I made a mistake. This part of the molecule is not supposed to be there, but rather that part of the molecule is supposed to be here. And therefore, this is not an optical center. So therefore, the number of optical centers in norethindrone are 1, 2, 3, 4, 5, 6. 6 optical centers, and therefore the total number of optical isomers that norethindrone can have is 2 exponent 6. And 2 exponent 6 is equal to 64. Therefore, norethindrone can have 64 stereoisomers. For each of the following, draw the most stable chair forms. So let's consider the first molecule. You can see that. Let's try naming this molecule by assigning numbers to the carbon atoms in that makes up the cyclic ring. So you can see that this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4, 5, and then 6. Now, if we were to draw this in the form of the chair conformer, then you can see that between 1 and 2 is a cis relationship. So carbon number 1 and carbon number 2, they are cis. And then since they are cis, it is either an AE or an EA relationship. It's either we put the methyl group on an axial position and then the isopropyl group on an equatorial position, or the vice versa. But because the isopropyl group is bulkier than the methyl group, then the isopropyl group will be on the equatorial position, which is the most favorable position for stability. And therefore, this cis is going to be an AE. Now, you see that for the 1,4, it is also a cis relationship. So 1,4 is also a cis. And the cis relationship, chlorine is bulkier than a CH3. And therefore, this is also going to be an AE relationship. Then between the 2,4, if we were to draw this on the chair conformer, the 2,4 is the same as 1,2,3, a 1,3 relationship, and it is a cis. So 1,3 in a cis in a chair conformer is either an EE or an AE relationship. But because we are looking for the most stable conformer, therefore we must put all the substituents in an EE relationship. So let's go ahead using this information to draw the most stable chair conformer. So this is our chair conformer. carbon number 1 must be in the axial position. So this is, let's start from here. Carbon number 1, that is an axial position here. So this is the CH3. So the group on carbon number 1 must be on an axial position. And then carbon number 2 must be in the equatorial position. So carbon number 2 is in the equatorial. This is carbon number 2, which is a CH3 2. So this is an equatorial position. And then the carbon number 4 must be in an equatorial position. So this is 1, 2, 3, 4. So this must be in the equatorial position, chlorine. And this is the most stable chair conformer for this configuration. And the reason is because the two most bulky groups are all in the equatorial position. Now let's check whether the configuration is correct. You can see that between this CH3, this isopropyl group and the chlorine is a cis, and then it is a 1,3. So 1,3, which is a cis, is EE or AA. But you can see that this is an EE. So the configuration has not changed in the chair conformer. And then the 1,4 is also a cis, and cis in the 1,4 is an AE. And you can see that this is in the axial position and this is the equatorial position. And then let's also try a 1,2. 1,2 in a cis, 1,2 they are cis, and that is also an AE. So this is an AE. So the configuration has not changed in the chair conformer, and this is the most stable chair conformer. Let's come to the B. Now let's try labeling the carbon atoms. So this is 1, 2, 3, 4, 5, and 6. So 1, 2 is a trans. So let me write it here. 1, 2 is a trans. And trans in 1, 2 is an AA or EE. But because we are drawing the most stable chair conformer, we must put it on the EE. And then let's check for 1, 3. 1, 3 is a cis. And a cis in 1, 3 is either an AA or an EE. So this is a cis in chair conformer. 1, 3 cis is an AA or an EE. So we'll put this on an EE because we are looking for the most stable chair conformer. And then let's do for 2 and 3. 2 and then 3 trans. And because they are in trans, this 2 and 3 is the same as 1, 2. 1, 2 trans is an AA or an EE. But because we are looking for most stable chair conformer, we'll put it on an EE. That means that you see that everything here is an EE. So we'll just have to draw a chair conformer and put all the substituents in an equatorial position. So let me draw it here. So let's start from carbon number 1. This is carbon number 1. So the chlorine is in the equatorial position. Carbon number 2, which is the isopropyl group, it also has to be in the equatorial position. And this is CH3 2. And then apart from that, we come to carbon number 3. And this carbon number 3 is the CH3, and the CH3 has to also be in the equatorial position. So here is a CH3. So this is the most stable chair conformer for this molecule. Now let's come to the C part. Considering the C, you see that if we were to number them, so this carbon number 1, carbon number 2, carbon number 3, number 4, number 5, and number 6. So you can see that 1, 3, there are 6 molecules. And everything here is in 1, 3. So 1, 3, 6 is an AA or an EE. But we will use EE because we are looking for most stable chair conformer. And let's do for a 1, 5. The 1, 5 is a trans molecule. But this is a trans in an 1, 3. This 1, 5 is the same as 1, 3 because 1, 2, 3. And this is a trans in a 1, 3 in terms of chair conformer. And a trans in 1, 3 in terms of chair conformer is an AE or an EA. But because the chlorine is more bulkier than the CH3, we are going to put the chlorine in an equatorial position and put the CH3 in an axial position. And let's check for 3, 5. The 3, 5 is also a trans, but this trans is in 1, 3 in terms of chair conformer. But this isopropyl group is more bulkier than the methyl group. So the isopropyl group will be in an equatorial position and the methyl group will be in an axial position. So this is also an EA. So let's go ahead and draw the chair conformer. So for this one, I'm starting here as carbon number 1. And carbon number 1 had chlorine on it as its substituent. And we said carbon number 1 had chlorine on it as its substituent. And we said that must be in the equatorial position. So let's put this chlorine in an equatorial position. So chlorine is here. And then carbon number 3, which is 1, 2, 3, is the isopropyl group. And then we said that the isopropyl must also be in an equatorial position, which is carbon number 3. It must be an E. So we must draw this in an equatorial position, which is CH32. And then the last one is the CH3 group. And we said that the CH3, number 5, it must be in an axial position. So 1, 2, 3, 4, 5. This must be in an axial position. So the CH3 must be here in the axial position. So let's check whether we've maintained the configuration. This is 1, 2, 3. And then that is EA. And this EA in 1, 3 is a trans. And you can see that on the molecule, this 3 is 5. So it is 1, 5. This chlorine and then the methyl are on carbon number 1 and carbon number 5, which is a trans. So it is a trans here. And then 1, 3 here is a cis between the chloro and the isopropyl. And cis in a 1, 3 is an EE or an AA. But here is an EE. So the configuration is also the same. And then if we check here, 3 and 5. 3 and 5 is a trans. And 1, 3 in a trans is an AE or an EA. And this is an EA. So you see that we have not changed configuration in the chair conformer. And this is the most stable chair conformer because the 2 most bulky groups are in the equatorial position. This is the least bulky group, which is the CH3, and it is in the axial position. So this is the most stable conformer. So let's come to this molecule. So you can see that this is the correct labeling of the molecule. 1, 2, 3, 4, 5. So what's the relationship between the chlorine and the isopropyl? It is a 1, 3. 1, 3 in terms of chair conformer, and this is a cis. 1, 3 cis in a chair conformer is either an EE or an AA. But because we want the most stable chair conformer, we'll do an EE. And then 1, 5 in terms of, and this 1, 5 is a cis. In terms of chair conformer, this is a 1, 3. 1, 3 cis is also an EE or an AA. And let's come to 3,5. 3,5 in terms of chair conformer is also a 6 because it is 1,3 in terms of chair conformer, which is also an EE or an AA, but we would use an EA. So that means that we need to draw a chair conformer and put all the substituents in an equatorial position. So let's draw it here. So I'm starting from here as carbon number 1. The chlorine must be in an equatorial position. And then on carbon number 3, the isopropyl group must also be in an equatorial position. CH3, CH3 2. So let me bring it down here. It is CH3 2. And then on carbon number 5, the methyl group must also be in the equatorial position. So this 1, 2, 3, 4, 5, which is here. So this methyl group must also be in an equatorial position. So you can see that this is also the most stable chair conformer because all the substituents are in the equatorial position. Draw the possible conformers of the compound below and indicate the most stable conformer. So that means we are supposed to draw this compound in a chair form. If we were to label the carbons, so this is carbon number 1, carbon number 2, and this nitrogen will be 3, 4, 5, and 6. If this is carbon number 1, then this is carbon number 2, but they are in the trans position. So we need to draw the trans, and then in the trans position, it is either an AA or an EE. So this is, and because we are looking for the most stable conformer, we need to put all in an equatorial position. So the carboxylic substituent CO2H will be in an equatorial position. Sorry, let me write it well. CO2H will be in the equatorial position. And then this substituent CH3 will also be in the equatorial position. Apart from this, we can also put both of them in an axial position. So let's draw the chair conformer again. So nitrogen is here. So this CO2H will be in an axial position. And then this CH3 will also be in an axial position. So these are the two possible chair conformers of this molecule. However, the most stable conformer will be this conformer, because in this conformer, both substituents are in the equatorial position.